Hi, welcome back. This time we're going to talk about calculating area inside regions that are defined through polar equations. I think it is useful to think back to the first time we were talking about calculating area um, under a curve in Cartesian coordinates. Now, uh, in that instance, we were calculating area as adding up a bunch of little bits of area. We broke down our region into a whole bunch of little tiny rectangles of width dx and of height f of x. And so when we were writing down area is equal to the integral of d area, then what we got was x, f of x times dx, where x goes from a to b. So that was when we were dealing with Cartesian coordinates. Now we can talk about the area under a curve, but when our curve is a polar function. So in that case, what does it mean to be under the curve? Well, what it means to be under the curve, so we have this function that's defined, r equals f of theta. Under the curve corresponds to being between the curve and the origin. So we've got this little slice here where we're going from a theta is equal to alpha to theta is equal to beta. And what we'd like to do is we'd like to come up with an equation for what the area is inside this region. So when we're in this regime, the slices no longer look like rectangles. They look like little tiny, well, pieces of pizza, little tiny slices. So let me fill this in here. We've got these little tiny slices that are now just sectors of we can really think of them as a circle. So if I'm going to zoom in on here, what we have is we have a very tiny slice where we have a little d theta here. And the question is, how much area is there in a tiny little bit of this slice? Well, this is no longer a rectangle, and because it's not a rectangle, we can't use the formula f of x times dx, because that was our length times width. Now we're in one piece of a circle, where the angle of the circle is d theta, and the length of this circle is f of theta, or r, right? So just like in the previous case, when we're drawing this rectangle, we said a rectangle is really a good approximation for what we have here, even though the top of the rectangle is slightly angled. We still think of it as a rectangle basically because it's so skinny. So similarly here, even though we're not the curve doesn't sketch out a circle, we're in such a skinny slice that we can approximate this as one piece, one small bit of a circle. And so the question now becomes then, what is dA? So how big is dA going to be for this slice? So what we'll do, because we're thinking of this as part of a circle, what we'll do is we'll say the area of the slice if we take that and we divide by the area of the whole circle, So the area of the circle is pi r squared. That ratio is going to be the same as the ratio between d theta and the whole angle of a circle, which is 2 pi. So this is the angle of slice, and this is the angle of the circle. And so what that means is we can write this as dA is equal to pi r squared d theta over 2 pi, or in other words, it's r squared over 2 d theta. And so if we want to calculate how much area there is in this piece of, so under our polar curve, then what we get is that area is equal to the integral of d area. So in this case, we have theta goes from alpha to beta of r squared over 2 d theta. And so if we write that with f instead of r, then what we get is the integral from theta is equal to alpha, theta is equal to beta of f of theta squared over 2 d theta. Whoops, I'm in the way. All right, so let's do a quick example. Let's say we have an example like this. Find the area inside one loop of the 4-leaved rows r is equal to cosine of 2 theta. So let's use Mathematica to draw this picture and really understand what's happening better. All right, so remember in Mathematica, to get a picture of some polar equation, we use polar plot. And so we do polar plot of, our equation was cosine of 2 theta, where theta, well, we'll go from 0 to 2 pi and see if our picture completes itself, and you can see that it really does. So what we have here is we have this picture, and we can see what we're hoping to do is find the area of one of these pieces. So what does that mean? Let's now go back over and draw a picture, draw our own picture of this so that we understand a little better. So here's our picture, and we'd like to find the area of one of these pieces. So if you think about it, what are we doing? We are looking for the area underneath this curve, and so what we'll need to do is we'll need to figure out, well, what are the bounds on our theta, so that we can put it into our equation and solve for it. So step 1, determine the bounds on theta. And then later, step 2, take this integral from our first bound to our second bound of the function. So the function is cosine of 2 theta squared divided by 2 d theta. Calculate the integral. All right, so what is happening here? So with a lot of the questions in these sections, we're going to have to find, we're going to have to solve some trigonometric function trigonometric equations. So I've posted a couple of links to refresh your memory if it's been a while. But for example, in this example, what we're doing is we need to figure out where does this curve, when does it go through the origin? So if I'm going to draw in some lines here, what is our theta equals alpha? And what is theta equals beta? Those are going to correspond to when the function value gives 0. So when we're determining the bounds on theta, what we need to do is we need to answer the question, for which theta does the curve pass through the origin? Which corresponds to solving cosine of 2 theta is equal to 0. Because passing through the origin is the same as r is equal to 0. All right, so we're going to solve cosine of 2 theta is equal to 0. So when is the cosine function equal to 0? Cosine of theta is equal to 0 when cosine of a value is equal to 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Move that down here. So cosine of 2 theta equals 0 means that 2 theta is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, etc., which means that theta is equal to pi over 4, or 3 pi over 4, or 5 pi over 4, or 7 pi over 4, etc. And so what we're seeing here is that this value is going to be when theta is equal to pi over 4. And we kind of need to go backwards here. This is theta is equal to 0. And we could keep going and we could say, okay, well then this is going to be theta is equal to negative pi over 4. So that would be going this other direction here. So theta, when we're setting up our integral, we're going to take this integral from where theta goes from negative pi over 4 to positive pi over 4. So this is the integral we need to do. You could use some double angle or half angle identities if you want to. So maybe it would be good to review them. What I think we'll do now, let's actually go get Mathematica to do that calculation for us. So we'll switch back over. And what we want to do is we want to integrate cosine of 2 theta divided by cosine of 2 theta squared divided by 2, where theta goes from negative pi over 4 to pi over 4. And we get the answer, pi over 8. So that's telling us that the area inside this curve is pi over 8. Let's go back. So this integral we're saying is equal to pi over 8. And so let's think about what that value would be. That value is something like 3/8. So does that make sense? Well, if we think about this piece, it's lying inside a circle of radius 1. The circle of radius 1 has total area pi. So if we're looking at one of these 4 pieces, it appears that both these pieces, each of these leaves, and the little bits up here all have the same area, so pi over 8 does seem to make sense. All right, so let's stop here and see you soon.